Hi everybody. In this video we're going to continue the unification of science using nothing more than standardized language. In the last video we looked at the language right at the heart of classical physics, curvature of space-time, and we saw just how inappropriate that word is. If all the satellites going around the Earth suddenly lost linear momentum, they would all fall in perfectly straight lines down the density gradient heading towards the centre of gravity. Straight lines, no curvature, none. This video I'm going to expose the other language problem right in the heart of classical physics, and that is the current explanation for electromagnetism. Magnetic bodies and fields, gravitational bodies and fields, electrical bodies and fields, they're all the same principle, but we've got very different language. Electromagnetism is called a fundamental force, and that's where it gets misleading, the word force. If we go over to classical mechanics, what we find is the need for physical contact before we can apply a force. Physical against physical. Levers in which I exchange force for distance. Gears. We exchange rotational distance for force. It is something that gets changed. Pneumatics and hydraulics, area, physical contact between gases and liquids. It requires physical contact to apply a force. But magnetic bodies and fields, magnets don't touch other magnets, but the magnet still moves. And it's not because of the magnet, it's because the magnet, the other magnet, is connected to the field. So I can't have the same word for two completely different principles. Physical matter and empty space cannot have the same word as physical matter against physical matter. So you see the problem that we're in. So it's not for me to decide what language we're going to use. It needs to be an organisation with people from every different field of science who get together and standardise the language we've got that describes reality. If we look at classical physics, there's three main parts. So now we've got the relationship between physical matter and space, gravitational bodies, magnetic bodies, electrical bodies and their fields. And that needs a name, the three of them together, because they're all linked by the same principle. And then we've got classical mechanics. And very important to look at the word mechanics. It means parts against other parts. Very different from parts against empty space. So we've got to stop using the word quantum mechanics for all of it. That's quantum mechanics is a subset of quantum physics, just as classical mechanics is a subset of classical physics. And the other kind of relationship we've got, the classical scale, is matter, physical matter, solids, liquids and gases, and waves of energy. So wave mechanics. And now we can see we've got it grouped in threes, and each three is 3. Why 3? Well, it's a very, very important number because it's the second prime number, and it's all you need to get everything else. 3 colours, you get everything else. 2 prime numbers build the number system. Really important to grasp that at base, the universe is a mathematical structure, and we can't see it. That's going to take some time to sink in, but here's a book. Mathematics in Nature. None of these mathematical patterns are in any physics book. Explain that. Well, this series of programs is going to explain that in clear, simple language. So now we've got to think of a correct word for the relationship between physical matter and space that describes their relationship. Is it going to be general relativity covering all three? I don't know, it's not for me to say. But it is time to move on to something much, much better. Now, to get the foundations all in place, we've got to look at these laws here. Laws of chaos. Nobody suspected that these laws would even exist, that there would be common mathematical principles for chaotic systems. Nobody suspected it. And it caught the scientific community completely by surprise. So what we've got to do now is to find some way to give a common explanation for these two. Classical physics. Fundamental physical behaviour. But is it going to be chaotic physics? Once again, it's not for me to decide, but they are fundamental. They do not emerge from classical physics, just as classical physics does not emerge from quantum physics. These rules are very, very important. Let me read first page of the book for you. Why have scientists, engineers and mathematicians become intrigued by chaos? The answer to that question has two parts. 1. The study of chaos has provided new conceptual and theoretical tools enabling us to categorize and understand complex behavior that had confounded previous theories. That means physics. 2. Chaotic behavior seems to be universal. So if you're studying interdisciplinary science, you need to read this book. First page of the book. Chaos shows up in mechanical oscillators, physical systems, electrical circuits, lasers, non-linear optical systems, chemical reactions, nerve cells, biology. This is it. And this book gives us the answer of how nature gets beyond the laws of physics. This is going to be very important. So, page 46. Here we go. These features, and that means chaotic features, seem to be largely independent of the physical, chemical, or biological details of the system under investigation. Independent. This mathematics transcends physical reality, and that means everything in terms of energy. So we don't need to consider the second law of thermodynamics. So what's the real difference? Well, if we look in this book at harmonic pendulum, I just look at the properties of the pendulum, measure the length of the arm, and I can determine the behaviour, the rate of swing. With a chaotic pendulum, I can't do that. The two arms, the lengths of them, the relative lengths, are changing microsecond by microsecond. It's dynamic. It's an emergent behaviour which emerges from the relationship in between the two arms, not because of properties of the arms. Emergent because of the relationship. The relationship can't be measured in terms of energy. It's got nothing to do with the components. So, harmonic pendulum, reductionists, just look at the components, measure them. Chaotic pendulum can't do that. That's very, very important. Emergent behaviour. So I've got three fundamental sets of rules. Quantum physics, classical physics, chaotic physics, if that's what we all agree we're going to call it. Physical behaviour of matter, it is. All proved by experiments, it is. It's bedrock science. So we have to take it on board. Nature starts off as physics. So, behaviour of atoms, hydrogen in space. If you look at the clouds of hydrogen in space, say the Eagle Nebula, what you notice, and somebody has to tell you, there are no mathematical patterns. None. They're all different. As soon as the universe starts to self-assemble, we get spheres and arithmetic, prime numbers, holding the sphere in a state of existence. I get geometry and arithmetic building each other. To make the star light up, it's first got to make deuterium 2, the first prime number, and tritium 3, the second prime number. And then it makes the first composite nuclei and the first composite number 4, helium. But unless somebody points out the mathematics building itself, we don't notice the mathematics coming up in the sky every morning. You need somebody to tell you. Well, now I've told you. And what we notice, the matter starts to climb a complexity gradient. And what we need is the mechanisms. Well, I've just explained the mechanisms of how a chaotic pendulum is different from a harmonic one. But now we need to look at the self-organization of systems, starting with the solar system. A self-assembling, self-organizing clock. There must be a mechanism, a blind watchmaker. And there is. That's coming up in the next video. And if you're looking at biology in terms of systems, this is the one for you. Because biology is not based on random mutation. Cannot be. In the lifetime of the whole universe, you would not get one single protein by random processes. So pay attention to the next video and think about the language. We've got to get common language for the relationship between physical matter and space. We've got to get common language for laws of chaos. Are there physics, chaotic physics? We've got to choose. So if you're at university and you want to be involved in this language change, you can get in contact with me and we'll do something about it together. See you next time.